Good afternoon and welcome to the CERIAS Computer Security Seminar from Purdue University. Our speaker today is Dave Keppler from the MITRE Corporation. His topic will be transforming applications for vulnerability resilience. Dave?
Thank you. Okay, I'm going to be giving a talk about some research I'm doing at MITRE. General problem we're trying to solve is lots of applications out there, lots of vulnerabilities in them, people attack them all the time. The main problem is attackers can predict what you're running, they know what software you have, they can test offline, craft their exploits as much as they want until they finally get something that works, and they can use that same attack to compromise a wide range of systems across an enterprise. So our current defenses today are inadequate in this kind of an environment. A lot of things like our antivirus software and IDS filters, they're trying to search out bad things that we know about. Won't catch new exploits, won't catch very targeted single-use exploits. As well as after that is trying to write software that simply has less vulnerabilities in it. Well, that's pretty slow, very expensive, doesn't do anything for the software that's already out there. And also related to that is this idea of a patching treadmill, constantly trying to catch up to where the attackers are, trying to stay ahead of what they know about the exploits. And other things, brittle perimeters like firewalls, VPNs. All an attacker needs to do is find one way around that, and then they have full access to your systems. So observation that I've made is these actual vulnerabilities are pretty constraining on the attacks. The attacks themselves are quite fragile and rely on predictable attributes of software. Things like memory addresses, location of data structures, how the stack is constructed. A good example is the classic stack smashing code injection vulnerability. So we have a picture of a stack frame of a function on the stack, return address, some local variables, and some buffer. An attacker can overflow this buffer if they know where that buffer starts, how long it is, and where the return address on the stack is. They can craft this overflow in such a way that they can cause the function to execute the code that they've injected. The reason why this works is because they can predict those two things, where the buffer is, where the return address is, how much do they need to overflow. But none of those specific factors are implicit to the higher level functioning of the application. There's just implicit things that were picked by the compiler when the software was compiled down into machine code, or attributes of the platform that the code is running on. So our objective in this project is find ways to break those assumptions. We can perturb an application in small, relatively inexpensive ways, leave the application functioning identically. We'll change it just enough that it breaks attackers. Eliminates their ability to make assumptions about the state of your software. So there's been a fairly large amount of related work in this field. A lot of it stemming from the old fault tolerance work, Byzantine fault tolerance, isolating parts of a software, things like sandboxing, or old idea of multi-version programming, have separate teams write a piece of software to the same specifications. Ideally, they'll come up with different implementations that have different flaws. It won't fail in the same ways. A lot of hardening techniques out there, things like bounds checking on buffers that Java and C# and other languages like that use. The no execute bit on the stack to prevent the stack being treated as executable code. Other types of stack protections, implementing stack cookies, checking that they haven't been overwritten before you return, and other ways of reordering the way the stack is laid out in memory. All of these are things that can only be applied at compile time. The actual randomization factors, where they do exist, are fairly static. May only be chosen once when a program is actually executed. And also, another idea is just general diversity randomization, obfuscating the code. So we have address space layout randomization, changes where the stack begins in memory, where the heap begins in memory, or where libraries get loaded. Also another idea of instruction set randomization. You actually encrypt, transform the code of a function, dynamically decrypt it as it's executed. When an attacker doesn't know the correct execution key, they won't be able to inject code that decrypts properly into what they need. Another idea we've made use of is invariant programming. It's kind of a modification of multi-version program, like I mentioned before. But instead of having separate teams, we take one piece of software, transform it using some artificial transformation engine, run each of the variants in parallel given the same inputs, compare the outputs, and if there's any kind of divergence, we know that an attack is probably underway. We make changes to the program so an attack can only work successfully on a single instance at once. So what we've been doing in this project is trying to extend that prior work. A lot of it's only focused on one type of vulnerability, usually code injection, and a lot of it only works at compile time. So what we want to do is defend against many different types of vulnerabilities. Code injection, obviously. We also want to deal with command injection, a good example of that being SQL injection on web applications, and also more generic attacks which just overwrite data within a program, like a privilege escalation that, say, overwrites the effective user ID of a session. And finally, we want to apply these defenses to existing programs. So if we're limited only to defending new programs, there's an enormous base of software that still remains undefended. So existing approaches, like I said, we have source code, compiles down to machine code, one piece of machine code distributed all over and executed. So whenever there are any kind of defenses, they're only injected one time and remain the same after. So what we're doing with this project is introducing a couple of extra steps into this deployment. So we have source code compiled down into machine code. We take that binary machine code, analyze it, and transform it. So we can do control flow analyses and data flow analyses on the program given its binary instructions, determine where data structures are, where the code is, how the stack gets constructed, and find ways to change that without altering the high-level functioning of the program. So one thing we've done is addressing SQL injections in Java web applications. So this kind of command injection occurs when a program has some embedded command language in it that's interpreted, and those commands get passed out to, say, a database or a command shell, things like that. And the general problem in this case is usually that the inputs from the user aren't filtered properly, get plugged straight into this embedded command and executed. So if an attacker knows what your command looks like, what the syntax of that command language should be, they can alter the intent of the actual query. So in this case, I have, say it's a standard username password kind of check in a web application. The attacker enters their username and a password. Poorly implemented code would just take those and plug them directly into the query. So in this case, the attacker, instead of just putting in their user and password, they write as their username, administrator, close the quote, and then alter the add some additional SQL keywords, in this case just and true, then comment out the rest of the string after that. So the final query that ends up going to the database just tells the web application I'm the administrator, never does the password check. So our solution here is analysis and transformation. We take a compiled Java program, its class files and jar files, input them into this transformation tool, disassemble the Java bytecode into an intermediate representation that we can analyze, go through this code looking for signatures of SQL execution statements, the standard Java database APIs calls, backtrack from those calls to find all the fragments of strings that went into constructing that query. So the parts of the string which correspond with the actual SQL keywords, like select, from, where, that define the way that query works, are going to be in relatively static strings throughout the program, concatenated with user inputs here and there. So we can find those static pieces of strings, transform them in a way that the attacker can no longer know the correct SQL language, then output the transform version of this program with this applied. I can get my mouse over here. I'll go in depth a little bit more. I said the general idea here is an instruction set randomization. So we have our basic initial SQL statement, takes user inputs directly in. So normal injection can just alter that statement however they want. Now if we randomize this, so now instead of select and from, we use some transformed pseudo-encrypted version. Now when the attacker goes to inject their command, now they're writing normal SQL and instead of the transformed version. So now instead of a successful injection, the attack's been reduced to a benign syntax error. So how we do this, on the left we have some example code. It's been compiled down into a class. We disassemble it into this intermediate representation using a tool called soot, which it's easy to analyze, static single assignment form. We can go through, look for particular function signatures, and then do backwards data flow analysis. So the result of our analysis, we find down at the bottom, we find the actual SQL execute sync. Trace backwards there from that sync to find how that string was constructed, all the string operations that went into it, and then find the string literals, the constant parts of the string that we want to transform. So we can trace back, find how all different parts of the string are concatenated until we find these static pieces. So once we have those, we can go back into the code and transform it. So now everywhere there was one of those static string literals, we wrap it in a transformation function. So now that string gets transformed by this function when the code's executed, ideally every time a new session comes in or a new query comes in. And then just before the query is passed off to the database, we do the reverse transformation and do a syntax check. Make sure that the query coming through is proper, well-formed SQL. If an attacker tried to do an injection, the reverse transformation wouldn't have occurred correctly, and we'd end up with a syntax error. Then we can block an attack before it actually gets out to a database, throw back an exception, stop the code. Let's go back. Using my mouse pointer. Sorry. So I got a small demonstration of this. Let me get my web browser over here. So I put together just a trivial little demonstration of a web message board. Log in as some user, have Alice, her password. Go in, we have various forums and topics. This isn't working well. So now one of those pages is vulnerable to a SQL injection. All the inputs about which form to list and which topic in that form to show are just done through unchecked input straight into the command line. So if you have the standard query was select as a password check, looks up the username and password of that user, compares their input with what's in the database. But the vulnerability is that one of the fields that's input never actually gets checked. So if instead of a normal input we use this SQL fragment that puts in that form name, closes the quote, and adds in an additional query to post the contents of the username password database. So on this thing down at the bottom is what the query that actually gets sent to the database. So the result here is a broken demo. Always happens. So now what would have just been the list of topics also ends up having the username and password database appended to it. So now in the other tab here I have transformed version. Yeah, that's what should have appeared. If we go back and do the go back and try to do the same injection again on this transformed version of the program. Now it noticed that some code was in there that wasn't transformed properly, and noticed that that union keyword wasn't a legitimate keyword in the transformed version of the query. So it just truncates the query at that point and only returns the legitimate contents of the database that should have been returned. So we can do that. This is a fairly trivial case, but we can do that for any Java program that constructs its SQL queries in a way that our analysis can handle any kind of program up to pretty reasonable levels of complexity. And as far as performance overhead, I think adding additional passes of syntax checking, randomizing text, doing find and replaces, ends up, when compared to the actual performance cost of going out to a database, interpreting SQL, returning it to a web application engine, constructing an HTML page, returning it to a user, utterly dwarfs the performance cost of doing this randomization. So it would have been a fairly expensive defense instruction set randomization and how it's traditionally applied to binary code as it's executing in a native binary, ends up being pretty acceptable performance for high-level interpreted language like SQL. So that's how we've dealt with command injection, particularly, in that case SQL, but you can also apply that same idea to any program that we can analyze sufficiently to do that trace back of command sync to user inputs and command construction. And for any command language that we have well enough defined syntax that we can determine what are the keywords, what are user inputs, what are data fields and do that transformation.
I have just one question. This is very interesting. How this entire approach may work when you have a web services, which can be dynamically composed? Yeah. So my question is how this entire approach would work when you have a web services which can be dynamically composed. So can you always trace back the creation of this?
Well, at some point, the web service is going to be constructed from some code.
Right.
It might be composed, higher level service might be composed of many smaller services. But as long as any of those particular services that talk to a database, we can take that piece of the larger distributed application, analyze it, and transform just that one component. Then we'll be able to defend, because if that's the only one that talks to the database, we've also protected everything else.
But what about doing this flow analysis? Can the flow analysis be limited to just that piece of code, or has it to go and look at other pieces of code?
Well, at the moment, all we do is, given a particular set of class files, compiled Java, to find it just goes through, finds all the standard Java database calls, the JDBC API, finds each of those calls in just that piece of code, and then traces back within that code to how the query was constructed. We don't have anything that traces across services.
Exactly.
Or
So
across
that was my
components.
question. So that.
Okay. So that's command injection. We also wanted to deal with more generic memory errors in like C, C++ kinds of programs, compiled native binary code. So one particular type of attack we were interested in, which hasn't gotten a lot of coverage in the literature, this idea of a pure data injection. So if you recall from earlier, the code injecting buffer overflow, the goal of that attack was to overwrite the return address of a function so that it jumped back to the injected code. But what if the goal of the attacker was only to overwrite the contents of those two local variables, x and y, that happen to be in the way? You can see this in a case if the function was doing some kind of security critical check, checking privileges, checking a user ID or password kind of thing. If you can overwrite just one of those variables in such a way that it alters the outcome of that function in a security relevant way, you can compromise the program in a way that a code injection defense that's only looking at the return address will never notice. So there's one good example of this in the literature. A couple years ago at Usenix, a paper was published about an attack that made use of a fairly old vulnerability in an FTP server that was originally a code injection. Use that same vulnerability to do a data injection, overwrite the effective user ID of that session. So instead of user whatever, it overwrites that user ID with 0 and becomes root on the machine using the same vulnerability. So the way we've tried to deal with this, there's many different types of vulnerabilities that can lead to this kind of data injection. First we had to try and categorize what are all those, and can we actually come up with defenses against them. So obviously buffer overflows are a big one. Another problem is uninitialized reads to memory. So if the contents of the stack don't get erased between function calls, some set of functions calls down, leaves all data on the stack, goes back up the stack, goes to further through the code to another function call, ends up using some portion of the stack. If one of the variables of that function isn't properly initialized before the value of some variable is used, an attacker might be able to alter the contents of that structure, control how the program goes on. Format string attacks, like a printf format string. It's kind of a bounds checking problem, except it's on the bounds checking the number of arguments to a function. So in certain cases, one of these attacks can lead to almost arbitrary random read-write I/O to the whole process memory space. So clearly we needed to deal with that one by bounce checking how the arguments get put into various types of functions. Then there's a whole wide range of heap-related errors, dangling pointers, double free kinds of things that can all lead to alteration of data on the application heap. So for each of these different types of vulnerability, we've tried to come up with different style of defending against that and a way of injecting that defense into an existing program. So just jump through them. Find my mouse again. So as far as buffer overflows, well, general way we defend against this is analyze the program, try to figure out, based on the code and how it executes, where buffers are in memory, what are the boundaries of those buffers, and then we try to insert checking code around any access to that buffer. So there's many different ways we can do this inference to figure out what parts of memory are buffers. We can watch as variables are read and written to as the code executes in a dynamic code translation environment. We can look at particular snippets of code, and based on certain heuristics, we can identify that this looks like a loop body that iterates across some kind of buffer, and we can identify what that some piece of memory is a buffer and what its bounds likely are. And general other types of data that might be there, debug symbols, anything else we can make use of in this analysis. So there's definite limits to what we can do with static analysis of a program in a binary case, especially with x86 instruction set. It's very difficult even to know if your disassembly of the code back into x86 assembly is correct. As instructions are variable length, you're not always sure where a function actually begins and ends. So what we've had to do is do a lot of dynamic runtime observation and analysis of the code. So our example here is some function, a couple of simple functions, do some math and multiplication. On the right is the x86 code that this function compiles down into. So based on this code, we can draw a lot of inferences, and also even more by watching it execute. So as the function goes through, pushes base pointer of the stack frame onto the stack, copies that to the stack pointer, allocates the local variable space for the function as an offset from the stack pointer. So now it moves the value 1 into some position of the stack. So now we know that that particular word of memory corresponds to an integer value, and we can use that later on. So at this point, then we can also trace that value back as it goes through registers again. So now we know that what the contents of the EAX register is, how that gets moved into another variable on the stack. See that the other function, the multiply function, is called. We know from the calling convention that how arguments are placed onto the stack, how the return value of a function comes back from a function call. So then when the top level function moves that value back into another one, we'll now also know that that third position is also an integer value. And then the standard semantics of other stack-related functions let us know how the rest of the stack is modified based on leaving the function the standard calling convention prologue. So for defending against format string attacks, like I mentioned, it's a bounds checking error on the arguments to things like printf that have variable length arguments. As the function ends up reading a certain number of arguments based on the contents of the first argument. So if an attacker can control the input to that first argument, they can control how far up and down the stack that function ends up reading. Certain of the format commands of printf allow it to write back certain things into memory based on one of these arguments. So combining all of that, in certain cases, you can get this read-write, random read-write I/O throughout the memory space. So the defense here, we found some work from SUNY Stony Brook that essentially does a bounds checking on that set of arguments. Go through here. So how it works is it can, based on how the stack pointer and base pointer gets modified as a function executes, and how we know that arguments for a function call end up being placed on a stack. So we can determine from the stack pointer anything below that to where the next function starts are going to be the arguments to that function. So what we do is take advantage of the hardware debugging flags built into the x86 architecture, make a second copy of the function arguments with a canary value placed in front of them. We set a hardware debug flag on that canary, so if ever code reads that, it'll cause a trap back into debug mode. The only thing that would, or no legitimate code would ever read far enough to hit that canary, but printf format string attack would try to read further up the stack than it should be, given that it should only have one argument. And for general memory errors, heap-based errors, a lot of these are due to the fact that the execution heap for most C libraries, the memory allocator, is quite predictable. Mostly they use linked list or doubly linked list implementation. The metadata for the size and the size of each allocated object, what objects are free, is kept in line with the data itself. So if an overflow allows you to overwrite an object, you can also affect the metadata that the stack allocator relies upon. And also because it's optimizing for memory efficiency, trying to pack as many objects into the least amount of space, ends up being fairly predictable about where in memory an object's going to get allocated. So an attacker can predict with pretty good accuracy that given some object, they can overflow into adjacent objects. So the defense here is to use a randomizing memory allocator. Sacrifice some space efficiency for more defense. So first we move all the metadata outside of the heap. There's no good reason why it should be in line with the actual user data. Just inviting trouble. So in the way this allocator works, it's the die-hard memory allocator, breaks up the heap into a variety of fixed blocks of different sizes. When an allocation request comes in, picks a block of the appropriate size randomly from its pool of available blocks. So every time an allocation comes in, it'll be directed to a different piece of memory. So now an attacker has no way of knowing that if they overflow object 2 by a certain amount, that they'll end up within object 3, overwrite stack metadata or the heap metadata in a certain way. So every time, for every different instance of a program, the overflow will act differently. The object will be in a different place. So that's roughly, well, pretty much the overview of the project so far. We're also exploring some additional things to do in the future. I said there's a very definite limits to what we can do with binary analysis, especially static analysis. You can only get so much information. Heavily optimized or obfuscated binaries, anything from commercial companies that's had packing or anti-reverse engineering kinds of tools applied to it, break all of our binary analysis techniques. So what we're hoping to do in the future is, given the success we had working with Java bytecode, look at similar types of more expressive instruction sets for kind of C, C++ programs. One we're particularly interested in is the LLVM compiler, low-level virtual machine. Uses a typed assembly language in a way as a internal representation throughout the compiler. Can also be treated as a bytecode in the same way as Java would be run through a just-in-time compiler virtual machine, in the same way that those higher-level bytecode languages give us lots more capabilities for analyzing code, determining what it is, where data structures are allocated, and make it very easy to transform code to get these kinds of randomization, statistically based defenses. So, thank you. Do you have any questions? Done? All right, thank you.